everybody, welcome back. So this is going to be our last video for Chapter 7, and we're going to be talking about the fundamental theorem of calculus, which we've talked about before, and now we're going to look at another application of its ideas. So before we start going through what the fundamental theorem of calculus says, let's look at this example problem to see if we kind of notice anything crazy happening when we combine derivatives and integrals. So if I look at this notation, it can be a little bit confusing. Let's think about it like this. The first step of this problem is going to be to evaluate this integral. So that's going to be step 1. And the second step of this problem is going to be to take the derivative of the answer that I get from evaluating the integral. So let's save the derivative for a minute from now after we're done with the integral part, and let's work on just evaluating the integral. And then we'll take the derivative of whatever we get. So in order to evaluate this integral, I'm going to need to start by doing an antiderivative. Now the antiderivative of cosine is sine of t plus c. And we're going to evaluate that between the lower bound, which is 3x, and the upper bound, which is x squared. In order to evaluate that, we're going to go ahead and plug in our bounds, starting with the top bound. So we're going to have sine of x squared plus c minus, we're going to have sine of 3x plus c. And we know from our experiences that when we simplify this and we distribute the negative, the plus c's are going to cancel. So what we're really going to end up with is that the next step would be to take the derivative with respect to x of sine of x squared minus sine of 3x. So now let's do that part. When we take the derivative of this, we're just going to take the derivative of each one of these terms one at a time. So the derivative of sine of x squared would be cosine of x squared times the derivative of the inside function, because we need to do chain rule. So it would be times 2x minus, and then the derivative of sine would still be cosine of 3x times the derivative of the inside function, which would be 3. Now what I'd like to do is compare our final answer to what we started with. If we pretend all this work didn't happen and we try to look for a connection between our original problem and our final answer, what you should notice is that in our final answer, we end up with a cosine function for both of these terms, just like we started with a cosine function inside of our integral. Now to get here, we used a sine function and then we did the derivative. But in the future, we're not going to do all that work. What we're going to do is just say, well, I know I'm going to end up with the same function that I started with. The only difference is that instead of just cosine of t, my first term has cosine of x squared plugged in, and that corresponds to the upper bound. My second function has cosine of 3x plugged in, and that corresponds to the lower bound. So if I'm trying to make connections between what I started with and what I ended up with, I'm going to keep the function the same, and I'm just going to plug in my upper and lower bounds. But then I also need to remember that I did chain rule. Now, when I did chain rule, what I saw was that I needed to attach the derivative of the bound. So this is the derivative of the upper bound, and this is the derivative of the lower bound. Now that's important because a lot of times students will make a mistake and think they need to do the derivative of the cosine part, but we're not doing chain rule for cosine. That's the outside function. We're only doing chain rule for the inside function, which is the bound. So if we turn this into a rule, In other words, can we create a rule that will allow us to take the derivative of an integral more efficiently? Here's what we would do. We would say anytime you want to take the derivative of an integral, you don't have to go through this big long process. What you can do is say, I know that my final answer will be the same original function with something new plugged in, minus the same original function with something new plugged in. And then here's what I'm going to plug in. First, I'm going to plug in B, and then I'm going to plug in A. But that's not all. After I plug those things in, I need to remember to do chain rule. So this would be dB dx, the derivative of B, and this would be dA dx. That would be the chain that I'm going to multiply by. So this is the original function from the integral. This right here is the upper bound. And this right here is the lower bound. This right here is the derivative of the upper bound. And this guy right here is the derivative of the lower bound. So in the future, instead of going through this process that we did up here, where we do the antiderivative, we plug in the bounds, and then we take the derivative, we're just going to skip straight to the answer. And we'll look at a couple examples where we do that on the next page. So let's go ahead and do that now. It says here, find dy over dx. So in other words, find the derivative for the following functions. Well, to find the derivative, dy over dx, I'm going to need to take the derivative of this stuff, this function that we had here. And to take the derivative of that function, instead of trying to do the antiderivative and then redoing the derivative, because I would need to do the antiderivative for the integral and then do the derivative because that's what it's asking me to find, I know now that I can skip straight to the answer. The answer is going to be my same original outside function with something new plugged in, minus my same original function with something new plugged in. So I'm keeping the sign the same here and here. Instead of having t squared, I'm going to plug in the x first. So I'm going to have x squared. And instead of, I am so sorry. Instead of t squared, I'm going to plug in the 4 next. So I would have 4 squared. Then I would do the derivative. So the derivative of x squared would be 2x. And the derivative of 4, oh no, I'm sorry, I did the derivative of the wrong thing. We're doing the derivative of x, not the derivative of x squared. I am so sorry. The derivative of the x would just be 1, and the derivative of 4 would be 0. So now let's look at how this simplifies. When we simplify this, here's what we're going to get. Multiplying by 1 doesn't change anything, so I would still have sine of x squared. Multiplying by 0 just turns that into a 0, so I don't need to write anything, and my answer would just be sine of x squared. Now let's try this problem, number 2. So, to take the derivative of y, I would need to take the derivative of this function that y is equal to. So what I'm going to do is I'm going to use my shortcut so I don't have to do this the long way. I'm going to leave the sine function the same. And I'm going to plug in, instead of t squared, I'm going to plug in my upper bound. So I would have 3x squared plus 7x squared. And instead of t squared, I'm going to plug in my lower bound. So I would have 4 squared. So here's my lower bound, and here's my upper bound. Then I would attach the derivative. So the derivative of 3x squared plus 7x would be 6x plus 7. And the derivative of 4 would be 0. So I'm doing the derivative of just the bound. So I'm looking back at the original problem and I'm attaching the derivative of the bound. 6x plus 7. Now I'm just going to simplify. So if I multiply these things together, I'm just going to have 6x plus 7 times the sine of 3x squared plus 7x squared. And when I multiply by 0, that just disappears, so I'm done. Now let's look at another example. So in the next example, we're trying to do the derivative again. Now the derivative of y would require me to do the derivative of this function that y is equal to. I have to take the derivative of this integral. So now I'm going to skip all the middle work and just jump straight to using my sort of rule, my property that comes from the fundamental theorem of calculus. And what that says is that the sine function is going to stay the same. And all I have to do is plug in my upper bound, which would give me 7 squared, and my lower bound, which would give me 3x plus 2 squared. And then don't forget to do chain rule and multiply by their derivatives. Now the derivative of 7 would be 0, and the derivative of 3x plus 2 would just be 3. Remember, I'm doing the derivative of the bound, so I'm going back to look at the original problem. Now when I multiply by 0, that goes away. It just becomes 0. So I'm just going to move the 3 to the front and make it a coefficient. Negative 3 times the sine of 3x plus 2 squared. And that's my derivative. Let's take a look at number 4. So for number 4, I'm going to have dy over dx is going to be the derivative of this integral. Now if I use the fundamental theorem instead of trying to do this the long way, I know that I'm going to end up with my cosine function with something new plugged in, minus my cosine function with something new plugged in. First I'm going to plug in the upper bound, so instead of t, I'm going to have x squared. Then I'm going to plug in the lower bound, so instead of t, I'm going to have 1. And the derivative of x squared would be 2x, and the derivative of 1 would be 0. Now, since I'm multiplying that last term by 0, it goes away. I'm just going to move the 2x to the front to make it a coefficient, and I would have 2x times cosine of x squared. We're going to go ahead and stop there and save these other examples for in case we need to go over some more stuff in class tomorrow, and we're going to skip to the second way that we can apply this idea, which is what else can we use the fundamental theorem for? So let's say I ask you to solve this differential equation with this initial value. So before I show you how to use the fundamental theorem, let's review what we already know. We know that to solve this differential equation, first I would separate the y's and the x's. So I would have dy equals secant squared of x dx. Then I would integrate on both sides to do the antiderivative. Now the invisible number next to the dy is a 1, so step 2 would be just having the antiderivative, which is y. The antiderivative of secant squared would be tangent of x plus c. Then it says that my initial value is pi over 4 comma 5. So now I would plug in that initial value, and I would have 5 equals the tangent of pi over 4 plus c. Now the tangent of pi over 4 is 1. So c would equal 4, which means my final answer would be the function that I started with here with that c value actually substituted. So my answer would be y equals the tangent of x plus 4. Now, the fundamental theorem is going to help us solve differential equations, but it's going to help us solve specific types of differential equations. So what if I gave you a problem like this, but we didn't know the antiderivative of our function? For example, here I knew the antiderivative of secant squared was tangent. But what if I give you this problem? What if I tell you the derivative is tangent? I don't know the antiderivative of tangent. I don't know a function whose derivative would just be tangent. So how could you solve this? Well, in my mind, the first thing I would try to do is I would try to separate the variables and solve this. But when I do an integral to try to do the antiderivative, what I realize is I don't know the antiderivative of tangent. So I would leave it like this. Y would equal the integral of tangent of x dx plus c. Now you'll notice that this plus c is not inside of the integral, because if you think about where the c came from doing the antiderivative of tangent separately and then adding c. So here we would have to do the antiderivative of tangent separately and then add c. Now that isn't something I know how to simplify, so I would kind of be stuck. But now I have to try to figure out a way to make it satisfy this initial condition. So if I want to make it satisfy this initial condition, I know that when I plug in 3, I get 5. Well, 5 is the y value. And I'm going to have the integral from tangent of x dx plus c. And here's how we make this happen. This is sort of the trick you have to use. I don't know how to compute this integral, but I know that when I plug in 3, I want to make the answer be 5. So in other words, I need to make this integral disappear somehow. Now I know that the way to make an integral disappear is to make it so that the lower bound and the upper bound are the same number. So I'm going to make the lower bound 3, and I'm going to make the upper bound 3. That way this integral would just be 0. So c would just equal 5. So how can we set this up so it works all the time? Well, it turns out c ends up being this y value every time. And it turns out we want this integral to cancel by having the lower and the upper bound be the same every time. Otherwise, this is an unsolvable problem because I don't know how to do this integral. So the only way to avoid having to do it is to make it cancel. So what we end up doing is we end up saying that a function that I was looking for was y equals the integral of tangent of something, d something, and I'll explain where that comes from in a second, plus 5, because c ends up being 5. So I'm just using this red function with my c plugged in, just like I did here. I'm plugging in my c and I'm writing my new function, but my new function has an integral in it since I don't know how to evaluate it. I couldn't do the antiderivative, so it still has an integral there. And then here's the trick. Make your lower bound the x value you know you're going to want to plug in. And make your upper bound x. Because that way, when you plug in 3 for the x, this will go away. Now the only catch is if you use an x here, you can't use an x in here. So the last little thing we need to remember is that we have to change this inside variable to a t. Now let's see if this makes sense. Does it make sense that this function would meet this criteria? Well, if I plug in the number 3 for the x, I have the integral from 3 to 3, which means this goes away, and that I just get 5, which is what I wanted. When I plug in 3, I want to get 5. If I take the derivative, this integral is going to give me the original function, the tangent function, with x plugged in. So yeah, the derivative would still be tangent. So that is a function, even though it's a function defined as an integral, that meets those criteria. In general, if your derivative is this function, and you have this initial value, then you can say that the original function you were looking for is the integral from your lower bound should match your x of the initial value, and your upper bound should be x, because that way when you plug in a, it'll cancel the integral out. You're going to put your derivative function inside there and change the variable to a t, because we can't use x's in two places in the same problem. Plus, because this integral is going to cancel, your c value is always going to match your b value. So let's see if we can figure out how to apply this. This is another example of a derivative whose antiderivative I don't know. So if I were to try to solve this differential equation, I would need to know how to do the antiderivative of cosine squared of 5x, which I don't know how to do. So instead, I'm just going to use an integral to set this up. So my original function will equal the integral of cosine squared, and instead of 5x, I'm going to make that 5t, because I can't use x's in two places in the same problem, dt. My lower bound is going to be the x value from my initial value, and my upper bound is going to be x. And my plus c will be the y value from my initial value. Now you could rewrite this as minus 2. So you would have this integral minus 2, and you would be done. And the reason we can leave it like that is because we don't know the antiderivative, so we can just leave it like that. So how would you do the next one? Well, we don't know the antiderivative of sine cubed, so my function would be the integral of sine cubed, and I'm just going to change the variable to a t, dt. And then we're going to set up the bounds so it meets this initial value. So my lower bound is going to be my initial x. My upper bound is going to be the variable x. And then plus my initial y value, which in this problem is 0. Now, again, the reason we do that is because we don't know the antiderivative. So solving a differential equation all the way would require us to do an antiderivative. Like here, we did the antiderivative of secant squared, and we got tangent. Here, where we don't know the antiderivative, our final answer is still going to have an integral in it, and we're just going to set it up in a very specific way so that we don't have to worry about that initial value, so that it satisfies that initial value every time. Thank you guys so much for watching. We will definitely be practicing this tomorrow, and have a great afternoon.